Semiconductors and doping. A semiconductor has an electrical resistance that is intermediate between those of good conductors and of good insulators. The importance of semiconductors in present-day electronics stems from the fact that their electrical properties are very sensitive to very small concentrations of impurities. The most commonly used semiconductors are silicon and germanium. An atom of silicon or germanium has 4 valence electrons that act to hold the atoms in the regular lattice structure of a crystal. So here's a germanium atom, and those 4 blue circles, those are the 4 valence electrons. And they're organized in the lattice structure here. Germanium and silicon significantly change their electrical properties when a tiny amount of impurity, and it's going to be arsenic in this example, right over here, right in the middle. When that's introduced into the crystal structure, that is called doping the semiconductor. Arsenic has 5 valence electrons, shown right here. When arsenic is injected, which is called doping, into a germanium crystal, only 4 of its valence electrons fit into the bonding structure. That 5th electron, the red electron, and no, they're not different colors, we're just highlighting it so you know it's a donor electron, that is free to move like the electrons in the conductor, increasing the conductivity of the substance. Even small amounts of injected atoms can increase the electron concentration in the conduction band. Remember, you had your valence band down here, your energy gap, and then your conduction band up here. It can increase the electron concentration by 10 to the 3rd to 10 to the 4th. In this case, the conductivity will be due to negative charge motion. This material is called an N-type semiconductor, N for negative. Adding atoms with 3 valence electrons, like gallium, into a germanium crystal will create a hole. So we're showing the 3 valence electrons, and there's room here to take another electron in so everybody can have those 4 covalent bonds. What will happen is a neighboring germanium atom will send its electron there. That will complete the required 4 bonds with the gallium, but now this germanium has a hole or missing electron, so it has a positive charge. What could happen then? Well, let's put another germanium up here. That can send an electron to fill in the missing hole, leaving this guy positive now. So we have a positive charge moving through the lattice in that direction. So that's the movement of the positive charges as the electrons are going down. So the hole is actually acting as a positive charge that can move through the crystal. This type of semiconductor is called P-type, P for positive. The electrical conductivity is due to positive charge or the hole motion, which is moving in the opposite direction of the electrons. In general, both N-type and P-type semiconductors remain neutral, but charges are moving through their structures. In an N-type semiconductor, there are more electrons and locations in the crystalline structure. The negative electrons flow from location to location. In a P-type semiconductor, there are more locations than electrons in the crystalline structure. We can think of this as a positive hole moving from location to location, opposite the direction of the electron movement.